Well, hello there. This is going to be Chapter 5, The Principles of Relativity in the Restricted Sense. I have a feeling this is going to be a little more complicated than the other chapters because it's a little bit longer. But we'll see what happens here. Um, so I'm just going to go ahead and start reading and comment as we go along. So, in order to attain the greatest possible clearness, let us return to our example of the railway carriage supposed to be traveling uniformly. Remember that? I'm just like my pencil's railway carriage. We call it motion uniform translation, uniform because it is constant velocity and direction translation, quote unquote. Because although the carriage changes its position relative to the embankment, yet it does not rotate in so doing. Let us imagine a raven, a bird flying through the air in such a manner that its motion, as observed from the embankment, is uniform and in a straight line. If we were to observe the flying raven from the moving railway carriage, we should find that the motion of the raven would be one of a different velocity and direction, but that it would still be uniform and in a straight line. Expressed in an abstract manner, we may say if a mass m is moving uniformly in a straight line with respect to a coordinate system k, then it will also be moving uniformly in a straight line relative to a second coordinate system k prime, proving that the later is executing a uniform translatory motion with respect to k in accordance with the discussion contained in the preceding section. It follows that. Okay, I'm going to stop for a second. So he's just talking about two coordinate systems. Okay, you got one on the train as k, and the train's kind of a rigid, somewhat rigid body, and then a raven is another called k prime, a little bird flying, as another coordinate system. Okay, so if k is the Galilean coordinate system, then every other coordinates. Now Galileo is that telescope guy. So if k is Galilean coordinate system, then every other coordinate system k prime is a Galilean one. Okay, so you say not only the train but the ravens also got their own coordinate. It's Galilean, the same one. When in relation to k, it is a condition of uniform motion of translation relative to k prime, which is like the raven or the bird flying. The mechanical laws of Galileo and Newton hold good exactly as they do with respect to k. We advance a step further in one generalization when we express the tenet thus: if relative to k prime, which is the train and the raven, the bird, is a uniformly moving coordinate system devoid of rotation, then natural phenomena run their course with respect to k prime according to exactly the same general laws as with respect to k. In other words, the train is k and the k prime is the bird. Raven. This statement is called the principle of relativity in this restricted sense. So just saying, okay, you got one reference system like a ruler on the train, and a ruler. The raven's got a ruler in his mouth, or something like that. So okay, next paragraph. As long as one was convinced that all natural phenomena were capable of representing with the help of a classical mechanics, there was no need to doubt the validity of the principle of relativity. But in view of the most recent developments of electrodynamics and optics, it became more and more evident that classical mechanics affords an insufficient foundation for the physical description of all natural phenomena. At this juncture, the question of the validity of the principle of relativity became ripe for discussion and did not appear impossible for that answer to this question might be in a negative. Now, one thing to keep in mind that Albert Einstein's father was electrical. He was a business person, but he's also an electrical engineer or electrical. He worked in electronics, so he probably had an influence on. He may have had an influence on Albert Einstein because he's introducing electrodynamics here when he's talking about a train and a bird. Most people kind of don't think about that you know aspect of it. But I got my little alarm going off here, so I gotta try to finish pretty quickly. So Nevertheless, there are two general facts which at the outset speak very much in favor of the validity of the principle of relativity, even though classical mechanics does not supply us with a sufficiently broad basis for the theoretical presentation of all physical phenomena. Still, we must grant it a considerable measure of truth, since it supplies us with the actual motions of heavenly bodies with a delicacy of detail little short of wonderful. And I think he's talking about the Galilean coordinate system. The principle of relativity must therefore apply with great accuracy in the domain of mechanics, but that a principle of such broad generality should hold with such exactness in one domain of phenomena and yet should be invalid for another is a priori not very probable. So yeah, he's just saying if there's an error in some frame of reference, uh, you know, it's not accurate. So we now proceed to the second argument, to which, moreover, we shall return later. If the principle of relativity is, in a restricted sense, does not hold, then the Galilean coordinate system K, K prime, K prime prime, like another moving object, which are moving uniformly relative to each other, will not be equivalent for the description of natural phenomena. In this case, we should be constrained to believe that natural laws are capable of being formulated in a particularly simple manner, and of course only on a condition that from amongst all possible Galilean coordinate systems we should have chosen one, and he's using K0, of a particular state of motion as our body reference. And I think this K0 is basically using light uh, or electromagnetic waves. We should then be justified because of its merits for the description of natural phenomena, calling the system absolutely at rest, and all the other Galilean systems K in motion. If, for instance, our embankment were the system K0, then our railway carriage would be a system K, relative to which less simple laws would hold than with that respect to K0. This diminished simplicity would be due to the fact that the carriage K would be in motion, to say really, with respect to K0. In the general law of nature, which have been formulated with reference to K, the magnitude and direction of the velocity of the carriage would necessarily play a part. We should expect, for instance, that the note emitted by an organ pipe placed with its axis parallel to the direction of travel would be different from that emitted if the axis of the pipe were placed perpendicular to this direction. Now, in virtue of its motion in an orbit around the sun, our Earth is comparable with a railway carriage traveling with a velocity of about 30 kilometers per second. If the principle of relativity were not valid, we should therefore expect the direction of motion of the Earth at any moment would enter into the laws of nature, and also that physical systems in their behavior would be dependent on the orientation in space with respect to the Earth. For owing to the alteration in direction of velocity of revolution of the Earth in the course of a year, the Earth cannot be at rest relative to the hypothetical system K0 throughout the whole year. However, the most careful observations have never revealed such anesiotropic properties. Uh, Alexa, define anesiotropic. Alexa, define anesiotropic.
From Wikipedia.org. The term tropic is from ancient Greek tau rho omicron pi iota kappa sigma, tropicos, in the sense of or pertaining to a turn or change, meaning causing a change, affecting. This is the same origin as tropic and trope.
Okay. Let me ask this other assistant.
The mic's off.
Oh.
The mic's back on.
Okay, hey Google, define the word anisotropic.
Here's the definition of anisotropic: of an object or substance, having a physical property that has a different value when measured in different directions. A simple example is wood, which is stronger along the grain than across it.
Okay, interesting. Anisotropics in terrestrial physical space. In other words, to say a physical non-equivalence of different directions. This is a very powerful argument in favor of the principle of relativity. So yeah, basically, he's just saying that because there's a lot of different velocities and a lot of different directions, the Earth is rotating. Earth is going around the sun's going around the galaxy is going around something else, and who knows what else, you know. Uh, so that's this chapter, and next chapter is chapter 6, theorem of the addition of velocities employed in classical mechanics. So I'm going to stop here because I have to go somewhere, but I hope you enjoyed this and maybe you learned something. Maybe take care.